Welcome to AI Podcast. I'm David Chen, and today we're turning a dense research paper into an easy, thoughtful conversation. The paper is titled LLaMA, Open and Efficient Foundation Language Models from Meta AI. If you only take one thing away, it is this. The researchers show that smaller language models trained on lots of publicly available text can match or beat much bigger systems on many benchmarks while being cheaper to run.
That's a strong opening, David. Smaller and cheaper, but still competitive. Can you give me the quick version before we dig in?
Absolutely. Meta's team trained a family of models from single-digit billions of parameters up to around 65 billion on roughly 1 trillion tokens or more. Because they trained longer on more data, these models perform surprisingly well. The 13 billion model often outperforms GPT-3, which is far larger, and the 65 billion model lands in the same ballpark as heavyweight systems from Google and DeepMind of that era. The payoff is lower cost at inference and easier deployment.
Got it. Who led the work?
The paper is led by Hugo Touvron at Meta AI, with colleagues including LLaMA among the core authors. It is very much a Meta AI effort.
Great. What problem were they really trying to solve?
Before LLaMA, the field kept pushing to ever larger models. That brought strong results, but also two issues. First, many models were trained on data that was not clearly documented or shareable, which limited reproducibility. Second, the community learned that for a fixed training budget, you can often do better by training a somewhat smaller model on more tokens. That idea is sometimes called compute optimal scaling. LLaMA asks whether smaller models, trained longer on only public data sources, can deliver state-of-the-art quality while being easier and cheaper to run.
So the gap they targeted was openness and efficiency, not just raw performance.
Exactly. They wanted strong models that researchers could study and deploy more easily, and that do not require stadium-sized server farms to serve.
What did earlier research get right, and where did it fall short?
GPT-3, Palm, Chinchilla, and others showed that scale works. But several relied on data that was not fully open or reproducible. On the open side, projects like OPT, GPT-NeoX, and Bloom were important for the community, yet at the time they trailed the top proprietary models on many benchmarks. Another gap was attention to inference cost. Training is one thing, but running a model for real users is a different budget. LLaMA aims to be competitive while improving the serving profile and telling a clearer data story.
What is the core idea they pursued?
The idea is simple. Smaller models can punch above their weight if you train them on more tokens and make a few careful design choices. The team uses a decoder-only transformer with tweaks like RMS norm, a SWI-GLU activation, and rotary positional embeddings. They also build a serious data pipeline from public sources, filtered Common Crawl, C4, Wikipedia in many languages, code from GitHub, Stack Exchange, academic papers from arXiv, and a books mix. Then they train for a long time with a modern optimizer schedule and a lot of engineering to keep things efficient.
Quick pause on that phrase, publicly available. Does that mean everything is cleanly licensed for model training?
Good question, and it is nuanced. Publicly accessible does not always mean the licensing is straightforward for commercial use. One of the components is Books 3, which later reporting linked to shadow library sources. So while the paper emphasizes public availability, the licensing picture is more complex. That debate is still active in the field.
Thanks for saying that out loud. How did they test whether this recipe actually works?
They evaluate across a wide range of tasks: common sense reasoning, reading comprehension, closed book question answering, math word problems, code generation, and a broad knowledge test called MMLU. Most evaluations are zero-shot or few-shot, which means the model has to generalize from minimal examples. They also run a small instruction tuning experiment to make the model follow directions better, and they probe safety-related behavior such as toxicity, bias, and truthfulness.
So this is not a single cherry-picked benchmark. It is broad coverage.
Exactly. and they compare against the usual references of that time, including GPT-3 and other large models, plus strong open baselines.
What did they actually find?
The headline result is that the 13 billion model surpasses GPT-3 on many of the benchmarks they report, which is impressive given the size gap. The 65 billion model is competitive with much larger systems on a number of tasks. On math, performance improves further if you use majority vote sampling. On code, the larger models show solid pass rates on standard coding tests. For broad knowledge like MMLU, the base models are good, and a short round of instruction tuning pushes scores noticeably higher.
That sounds compelling. Any caveats I should keep in mind?
A few. Benchmark comparisons across papers can be tricky, since small differences in prompts and scoring can shift results. The team also notes that toxicity can increase with model size, which is common, and toxicity scores depend on the exact measurement tools. Bias results are mixed across categories, and truthfulness is still imperfect, which is another way of saying hallucinations remain a risk.
Right. Bigger is not automatically safer or more truthful. What about practicalities? Can people run these models without a giant cluster?
Yes, and that is part of the appeal. The smaller LLaMA models can be served on a single high-end GPU, and even the larger ones are far more manageable than models that are many times bigger. That said, fully reproducing the training runs still requires serious compute and engineering. Training for weeks across thousands of top-tier GPUs is beyond the reach of most labs.
So it is easier to use than to rebuild from scratch.
Exactly.
Let's zoom in on the experimental design for a moment. Any assumptions or choices worth calling out?
Two stand out. First, data curation. They apply aggressive filtering and deduplication for web crawl content, and they mix in curated sources like Wikipedia, code, forums, research papers, and books to broaden knowledge and reasoning. Second, the architecture is conservative rather than exotic. They focus on training duration, token count, and efficiency tweaks. For evaluation, they rely on zero-shot and few-shot setups and use established scoring practices for multiple-choice and code tasks.
Now, the critical perspective. If you were reviewing this paper, what would you push on?
I would start with reproducibility of the exact dataset. Even if all sources are public, replicating the precise filtered snapshot is hard. The paper describes the pipeline, but does not ship a frozen copy. I would also ask for stronger contamination checks, meaning confidence that benchmark test questions did not slip into the training data. Next is licensing clarity. The field needs better norms, data sheets for datasets, and more licensed or opt-in corpora to avoid ongoing disputes. Finally, safety. The team reports preliminary toxicity, bias, and truthfulness results, and I would like deeper analysis and stronger post-training alignment.
Fair points. And what about environmental impact?
They report the energy use and estimated carbon footprint of training, which is good practice. It is a reminder that efficiency matters not just for cost, but also for sustainability. There is room to explore more efficient architectures or distillation to bring that footprint down.
Where does this leave us? What should the community focus on next?
4 directions. First, data transparency and licensing, with clearer manifests and stronger documentation, and more licensed or opt-in sources. Second, evaluation rigor, with shared prompting standards, contamination audits, and reporting uncertainty across prompt seeds. Third, alignment, moving beyond light instruction tuning to reinforcement learning from human feedback and safety-oriented fine-tuning, so models are more truthful and less toxic. Fourth, efficiency, through techniques like mixture of experts and distillation to cut serving costs and carbon while keeping quality high.
And for practitioners listening now, what is the practical takeaway?
If you care about performance per dollar at inference time, do not overlook smaller, well-trained models. With the right data and schedule, they can deliver most of what you need at a fraction of the serving cost. And when you evaluate open models, Look closely at the data documentation and the evaluation setup before drawing conclusions.
That is clear. Before we close, can you restate the main point in one sentence?
LLaMA shows that carefully trained, smaller models built from broadly accessible data and smart engineering can rival much larger systems and make state-of-the-art language modeling more practical to use.
That wraps today's AI podcast. If you found this helpful, share it with a friend who wants the signal without the noise. I'm Maya Patel.
And I'm David Chen. Thanks for listening, and we will see you next time.